So 3.4 is about the second derivative test for concavity. So the first derivative test tells you about whether something's increasing or decreasing, and the second derivative test tells you about whether a function is concave up or concave down. So let me define those two words, terms. I'll give you kind of the greeny definition and then the more math definition. So a function is called concave down on an interval if the function bends downward. That's the weak definition. But it's good. So concave down means the graph of your function is bending down. As far as pictures go, you want to think of something like this, maybe? If you compare this to a straight line, you can think of it as a line kind of bent downward. Mm-hmm. Or another way to draw a possibility for concave down might be something like this. Again, if you think of a straight line, this guy would be bent down. Concave up, the function is called concave up if what? Bends upward, right? Concave up on an interval if the function bends upward. So these guys are concave down. I'm going to draw concave up. Easiest example might be an upward parabola. Concave up. If you imagine a line, you would have to bend it upward to turn it into this. And then sort of a similar example to this, which is a slightly different looking concave up function. And if you think of a slanted line, you'd have to bend it upward to turn it into this. The technical definition, I'll write it quickly, I won't use it very often. Function is concave up on an interval if its derivative is increasing on that interval. Concave down if the derivative is decreasing. Let's start with down. Function is concave down if the derivative is decreasing. Concave up, the derivative is increasing. So does that make sense with this picture? If you look at this guy first. This is concave down, so as I move from left to right, the derivative, the slope of the tangent line, should be decreasing. So if you look here, the slope is very positive. But if you move forward a little bit, the slope is less positive. And if you move forward even more, the slope is less positive. So the derivative is decreasing because the slope of the tangent line is getting less and less positive. Mm-hmm. here the derivative is increasing because the slope of the tangent line is getting more and more positive, right? Here it's a little bit positive. Here it's more positive. Here it's much more positive. So here the derivative is increasing. So this is a helpful definition when we start doing math, but this is kind of a better, whether it's bending upward or bending downward is a little bit better for the graph. By the way, I said if the derivative is decreasing. So when a function is decreasing, its derivative is positive or negative? When an original function is decreasing, what can you say about the derivative? This is from 3.3. Right, when we did our little test, our little first derivative test, when did we draw an arrow going down? When the derivative is negative, right? So a function is decreasing when the derivative is negative. And the function is increasing when the derivative is positive. So f prime positive. But this is saying that f prime is increasing. And f prime is decreasing. So f prime will be decreasing when what? So f decreasing means f prime negative. F prime decreasing means f double prime negative. Right? Because you got to take the derivative of the derivative. It's like we have to take the derivative of f here. And f prime increasing means that the derivative of f prime, which is f double prime, is positive. So when we do concavity, when we start trying to figure out whether our function is bending upward or bending downward, we're going to have to look at the second derivative. So everything you do with concavity, everything you do with concave up and concave down, comes from the second derivative. So that's why it's the second derivative test for concavity. Sometimes, one more definition before we do that. Sometimes your function changes from concave up or from concave down to concave up. So for example, if you think about the x cubed function, this part of the x cubed function is bending downward. But right after you go through 0, x cubed starts looking like this. This part's bending upward. Right, so x cubed changes from concave down to concave up when x equals 0. So this point here where you change from one concavity to another, this is called a point of inflection. Point of inflection is a point where a function changes from concave up to concave down or vice versa. Function changes concavity. Where do you think points of inflection, how would I get at an x value for a point of inflection? Right, because the idea here is when you're concave up, f double prime is increasing, f prime increasing, f double prime positive. So concave up, f double prime is positive. Concave down, f double prime is negative. here f double prime is positive, here f double prime is negative. So you change, when you change, you have to be equal to 0. Or I guess undefined technically. So points of inflection come from the critical numbers of the first derivative. They come from where f double prime is 0 or undefined. Let me write this. Second derivative just for So when you test for concavity, when you're trying to find whether a function is bending up or bending down, which is going to help us graph, first thing you do is find the critical numbers of the first derivative. Now that's kind of silly. Find the critical numbers of f prime. That means the same thing as setting f double prime to 0 or undefined. Set f double prime to 0 or find where f double prime is undefined. Just like before, if you have a point of discontinuity, you want to include that in your critical numbers list. Include x vowels where f is discontinuous. So like if you have a vertical asymptote. You could possibly change concavity at a vertical asymptote, so you have to include those discontinuities in your critical numbers. Once you have your critical numbers, you test the regions. By plugging sample points into the second derivative. And kind of the same conclusions, well, similar conclusions to the first derivative test hold here, right? If you get a positive region, right? So if f double prime is positive, that means your original function is concave up. Right, so it looks like it bends upward. If f double prime is negative, it's concave down. And then whenever you change from positive to negative or negative to positive, whenever you change signs at all, you have a point of inflection. How you test for concavity. It's all the same stuff we were doing, except now we're dealing with the second derivative. Let's do a couple of find all points of inflection. And discuss concavity. So whether the function is concave up or concave. So points of inflection in concavity always have to do with second derivative. Right, so if you're asked for either one, a point of inflection or concavity, you know you're dealing with the second derivative. Start with a good old polynomial. X to the fourth minus 6x squared. I want to know where this guy bends up and where he bends down. Yeah, you're going to need to somehow get your second derivative. You're going to get your first derivative. So when you start this guy, you do f prime. The derivative is going to be what? 4x cubed minus 12x. Now, if I were looking for increasing, decreasing, or relative max, relative min, I'd set this equal to 0. But I didn't ask for that, so I'm not going to waste my time. I asked for concavity, so I'm going to move on to the second derivative. So what's the second derivative?
12x squared minus 12.
So you do the derivative again. The 3 comes down, the x becomes a 1. So 12x squared minus 12. So for my second derivative test, I figure out where this is 0 or undefined. It's never 0. I'm sorry, it's never undefined, but it is 0. So I have to set f double prime equal to 0. So I'll solve 12x squared minus 12 equals 0. Add the 12. 12x squared equals 12. X squared equals 1. So x is equal to
Minus 1.
excellent. So those are my critical numbers for the first derivative, or the possible points of inflection. Now I test. So I put a -1, positive 1, and plug in. Yeah, so -2, 0, positive 2. But because I'm testing for concavity, what am I plugging this into?
So the double prime.
Second derivative. So I put -2 back into my second derivative here. So 12 times 4 will be 48 minus 12. This guy will be... So when you plug in -2, it's positive. Okay, now when you test for concavity, you have to be very careful how you do your chart. You only do 2 symbols, positive, positive, and then you put concave up.
He's happy.
Smiley face. That's technically correct. This is how all the books will do it.
Okay.
So when you put in 0, what do you get?
Negative.
Put in 0 to your second derivative, you get -12. So minus.
Looks upset.
Then when you put in 2, you get positive again. So you're happy.
Slightly disturbing.
So since I changed signs here, since I changed concavity, this guy is a point of inflection. P-O-I, and this guy's another point of inflection. If my sign stayed the same, if it were plus plus, then I wouldn't have a point of inflection. But they changed from plus to minus, from concave up to concave down, so I do. Alright, so let's see, concave up. What are my intervals that I'm concave up on? Negative infinity and -1, right, this interval here. Then I go concave down, so ignore that. Then 1 to infinity. concave down, -1 to 1. Points of inflection. So now I actually have to I have to plug some things in, right? Found concave up, I found concave down. But a point of inflection is just that, it's a point. So I have an x value. I need to get a y value. How do I get my y value?
Plug into the original.
Plug it into the original, right? You have to find f of -1. So go back to your original, plug in -1. So it'll be 1 minus 6, which is -5. So -1, -5 is 1 point that I change concavity at. Then also I have to do x equals +1, y equals f of 1. It's going to be the same thing, like -5. So, first of all, questions about it. Like I said, it's all the same stuff, just with second derivative. So don't pay attention. Really pay attention to these. Don't do anything with the first derivative if you're asked for a concavity function. Okay, so listen. No. Ooh, I like this one. F of x equals 2x plus cotan x on 0 to pi. What? What? At least it doesn't have any roots in it. You should hate roots. Just make everything difficult. So if I want to know concavity and points of inflection, what am I going to do here? Second derivative, right? Which means I got to go through the first derivative, unfortunately. So f prime is what in this case? 2 plus, what's the derivative of cotangent? So tangent is secant squared. So cotangent is negative cosecant squared. Cotangent, cosecant squared. Since I care about concavity, I gotta go again. Well, that's not too bad, right? Derivative of 2 is 0, so I don't care about that. But what about cosecant squared? How do I do the derivative? That's a chain rule, right? You have to think of this guy as cosecant x squared. Right? When the square is next to the trig function, you think of it as squaring the whole thing. So to do this derivative, it's going to be negative. The 2 is going to come out front. Then you subtract 1 from the power, so it's negative 2 cosecant x to the first times the derivative of cosecant. What's the derivative of cosecant? Cosecant, cotangent. Negative or positive? Negative. So the 2 came down. Subtract 1 from the power. That's why we got negative 2 cosecant to the first. But then we had to multiply by the derivative of the inside. The derivative of cosecant is cosecant, negative cosecant cotangent. So altogether here, f double prime of x is equal to
2 cosecant squared x cotangent x.
positive 2 cosecant squared x cotangent. Which when I'm doing critical numbers, I'm thinking about where the derivative is 0 and undefined. So you might want to change these into fractions. I would put these into sines and cosines. So cosecant 1 over sine, and cotangent is cosine over sine. So this will be 2 over sine squared x for this part times cosine over sine. So switching it into sines and cosines helps you find your critical numbers or your zeros and your undefined a little easier. So, I need to do two things. I need to know when f double prime equals 0 and when f double prime is undefined. So what do I do here? When is a fraction equal to 0? When the numerator is 0. So I set 2 cos x equal to 0. Divide out the 2. I need to know where cos x equals 0.
Pi over 2 and b pi over 2.
Yeah, now be careful because I gave you a slightly smaller interval than usual.
Pi over 2.
Yeah, so cosine is 0 between 0 and pi only at pi over 2. That's where my x value is 0. So this guy gives me one solution, pi over 2. Where's f double prime going to be undefined? That's when the denominator equals 0, right? So when sine cubed x equals 0, this cubed isn't doing anything because you can cube root both sides to get rid of it. So this will just be when sine is 0.
0.
Yeah, so sine is equal to 0 when x is 0, or when the angle is 0, or pi. Those don't make it in my interval. The only critical number of the derivative, place where f double prime is 0 undefined, is pi over 2. So what are we going to test? Yeah, well, okay. I guess it doesn't really matter. I would probably do pi over 4 and 3 pi over 4, but anything in between. All right, so let's do pi over 4 and 3 pi over 4.
2 over 2.
Yeah, so these go into the second derivative. The second derivative is right here. And again, I'm really only concerned about positive or negative, so you don't have to work too hard. If you put pi over 4 in here, you're in the first quadrant, so cosine's positive and sine's positive. So pi over 4, we get positive over positive. At 3 pi over 4, you're in the second quadrant, cosine's negative. So it'll be negative over positive. So I'm concave up from 0 to pi over 2. I'm concave down from pi pi over 2 to pi. And I have a point of inflection when x is equal to pi over 2 and y is equal to what? So I go over here to my original. I'd have to actually plug it in.
0.
So you do 2 times pi over 2 plus cotangent of pi over 2. What's cotangent of pi over 2? Cotangent is cosine over sine, right? So if you're at pi over 2, cosine is 0, sine is 1, so this is 0 over 1, which is 0. So my y value is just we think. Okay, good. Good, I like it when you think. Thinking blank means I'm definitely doing a good job. All right. Cool, cool. Cool. So let me give you a different type of example. Maybe I'll do some more of these next time. Maybe not. I don't know. These are boring. But let me give you a new example. All right. The second derivative test for concavity is not mind blowing. You do exactly the same thing as the first derivative test, except you do it with the second derivative. But I want to give you an example that gets you thinking about these graphs here and what concavity really means. So sketch possible graph for each function. So the first function here, f, has to satisfy the conditions f prime of x is greater than 0 on the interval negative infinity to infinity. This is one condition. We'll call this part A. F double prime of x is less than 0 on negative infinity to 0. And f double prime of x is greater than 0 on 0. So let's sketch we want to be able to sketch a graph of a function that has these three conditions. So there's a bunch of different answers, but how do you think you would break this down?
It's increasing.
Right, so think about what the first derivative and the second derivative tell you. The first derivative, positive, tells you that your function is increasing. And so because the first derivative is positive from negative infinity to infinity, my function is going to be increasing everywhere. So this function is always going up. So if I were going to draw, it's always going up. That has to be increasing. So that's not my function, that's just kind of a note, so I remember that. F double prime less than 0 on negative infinity to 0. That means at 0 I have kind of a change in behavior. And F double prime negative means concave up or down? Concave down. F double prime less than 0 is negative, so I'm concave down over here. F double prime greater than 0 means I'm concave up over here. So I have to fit these three conditions. My function always has to be going up, but it has to change from concave down to concave up right in the middle. Can I do this?
Execute.
Execute one. Now, so basically what you want to think of here, in order to always be going up, you can't actually turn around like this. Right? You're going to have to stop your concavity up at the top, like this. Otherwise, you start going down. So the fact that this is increasing means you want to stop your concavity like this and start your other concavity like this. So concave down. Concave down, looks something like that. Switches to concave up. And always increasing. These are kind of my notes. But this blue part is the actual possible sketch on function. So quickly, let me do a very similar one here, where I have I want it to always be increasing again, so we'll put this one the same as part A, same as before, but then I want to flip-flop these two. So I want it to be concave up on negative infinity to 0. And then concave down after 0. So because this first condition is the same as A, because I'm always increasing, my function always has to be going up. But also my concavity is going to have to max out at the peak here. So what I mean is this portion is concave up, which looks like this. But in order to always be increasing, I'm going to have to get rid of this part. Otherwise my function's not always increasing. Then over here I'm going to be concave down. But to always be increasing, I have to get rid of this part. Right, and I switch at 0. So for this first part here, yeah. Here, this guy's concave up, right? He's bending upward. But he never actually gets to a minimum and turns around. This guy's concave down, right? He's bending downward. But he never actually gets to that maximum. I'll just look at this blue last.
When did they both work?
This is one.
Wouldn't Q2 back work for the first one?
No, because they don't have cavity. Right, this guy's concave down, this guy's concave up. So one more then I'll let you know. So here's your conditions. 1, f prime of negative 1 equals f prime of 1 equals 0. F prime of x is less than 0 on negative 1 to 1. and then f prime of x is greater than 0. Otherwise, so, well, not quite otherwise, on negative infinity to negative 1, and 1 to infinity. F double prime of x is less than 0 on negative infinity to 0. F double prime of x is greater than 0 on 0 to infinity. So there are your conditions. So what does the fact that f prime of 1 and f prime of negative 1 equals 0 tell you? The derivative is 0, what do you know?
Graph as a
Max or min, right? Horizontal tangent line. Derivative being 0 means you have some sort of horizontal tangent line. Now, at negative 1 and at 1, I change as far as my derivative is concerned. From negative 1 to 1, f prime is less than 0, which means on this region, I'll be decreasing. But on negative infinity to negative 1 and 1 to infinity, f prime is greater than 0. So I'll be increasing. For concavity, I'm less than 0 on negative infinity to 0. So I change concavity at 0. And the concavity here says negative concave down on the left. Like this. It says positive concave up on the right. So it looks pretty good, right? It looks like you can piece that together. You have a max. I don't know where the max is. It doesn't tell me any information, but I know I go from increasing to decreasing to a horizontal tangent line. So I have a max somewhere. At 0, I change concavity, so I'm going to have a point of inflection somewhere. And then over here, I have a min. So maybe concave down. And I'll change concavity. Go down a little. Concave up. My horizontal tangent line with my max. Horizontal tangent line with my min. Concavity changes from up to down. Or from down to up, I should say. So this is what we're going to have to do in 3.6. We're going to have to take information about the derivative and the second derivative and try to put it together into a nice looking function. So on Wednesday, I'll do a couple review examples from 3.4, and then we'll jump into the graphing in 3.6.